Hello there, Mr. Sutton here with the BC Calculus 712 Extra Practice number 3 solutions on limit comparison test. For this one, we want to know which of these series can be used with the comparison test to determine if this series converges or diverges. So just in general, this series is going to behave pretty similarly to 2n over n squared, which is kind of like a 1 over n situation. This ought to behave just like the harmonic series in terms of converging or diverging. So it's probably going to diverge. Now, having said all that, which one of these series can we use with comparison to figure this out? And they say the comparison test. When they just say the comparison test, without really being more specific, they're talking about direct comparison. So we know that all these series are going to be positive, at least for n values of 1 or greater, which is all we care about here. So that's not really the issue. The issue is this has to be, this series which we think is going to diverge, we need to show that this is greater than the comparison series. So there's only one situation, one of these series, where we're going to be able to do that. So taking a look at this first series here, and by the way, with the comparison series, we would also like to diverge since we know this thing's going to diverge. So for this first one, 1 over radical n, well, this is a p-series with a p-value of 1/2. We know that's going to diverge because the p is less than 1. However, let's think about which one of these is greater. So again, we would like this thing to be bigger than this diverging series. So if we plug in 1, this is going to be 5 plus 2 over 1. So 7 over 1 is 7, and that's certainly bigger than 1 over 1. If we plug in 2, that's going to be 5 plus 4, which is 9. So we're going to have 9 over 4. So that's going to end up being, let's see, bigger than, well, I don't know what 1 over radical 2 is. Let's plug in 4. 4 is easier to take the square root of. So that would be 5 plus 8, so 13 over 16. And this versus 1 over the square root of 4, 1 over 2. So this is bigger than 1/2, so far so good. But we're actually getting closer in value now. That makes me a little suspicious. I'm going to do one more. Let's plug in 9 for n. If I plug in 9, this becomes 5 plus 18, so 23 over 81. This down here is going to be 1 over 3, 1 over the square root of 9. Well, 23 over 81 is actually less than 1/3. It's less than 27 over 81, which would be 1/3. And then if we keep going, let's plug in 16. 5 plus 32, that's 37 over 256. Well, that's way smaller than 1 over 4, which is what this would come out to. So the issue here is that the original series ends up being smaller than the comparison series as soon as n reaches 9, and maybe even before that, but that was the easiest one to see. So if you're trying to show divergence, showing that your series is smaller than a diverging series doesn't really prove anything. Your series might actually diverge or it might converge. We don't really know. So this is a no. We move on to the next one. So for this one, 2 over n, this can be shown by comparison to be just like the harmonic series, where you can actually just factor a 2 out of there. And then you have the harmonic series, which we know is going to diverge. Now, comparing these things, starting at 1, we've got 2 for this thing. This thing we said was 7. And if we keep going, does that trend continue? Let's plug in a big number here. Like, let's plug in 10. So we've got 5 plus 20, so 25 over 100, 1/4, versus this would be 2 over 10. So that would be 1/5. 1/4 is going to be, let's see, bigger than 1/10. So this ends up being smaller than the original series. So we have the order that we wanted. This series is positive and it's smaller than the original series. Since we've shown that a diverging series is smaller than the original series, that means the original must also diverge by direct comparison. So this actually works. Now let's just check out these other ones real quick. This one, 5 over n. So this diverges just like 2 over n did. If you take out a 5, this is just the harmonic series. The issue on this one is that if you compare this with the original fraction, well, this is basically the original without the plus 2n. So this is going to be, actually, I take that back. If you look at the original And forget about this 5, just kind of considering the limit as you go to infinity. This is kind of like a 2 over n situation. This is a 5 over n situation. So this is more like starting with a 5n over n squared. This situation would be. So that's going to be bigger than the original then. And you can see that if you plug in even just the n value 2, this original comes out to, let's see here, this would be 9 over 4, 9/4 versus 5/2. You know, that's definitely bigger than 9/4. Moving on to this last one, this one has a bigger issue. If you take out a 5 here, you've got 1 over n squared, which is a p-series with p greater than 1, which converges. So that one was a no. This one converges. And if you were trying to show convergence, you would have to show that this thing is greater than the original series. But this is just like the original series without the 2n. So this is actually smaller than the original series, which isn't very helpful for showing convergence. So this is also going to be a no. So at the end of the day, then, only choice B would work with comparison. For this problem, we're given the series -1 to the n plus 1 times some kind of mystery term that they don't really tell us a whole lot about other than the fact that it's greater than 1 over n for all n. And they also tell us that the sequence an decreases with limit 0. Okay, so we want to know what's true here. We're talking about whether this series converges absolutely, conditionally, not at all, or whether there's just not enough information to figure out any of these questions. So if this is a question of absolute convergence, let's first consider this series, the absolute value of this series, which is basically some value that is greater than 1 over n for all n. That being the case, since my term is bigger than 1 over n, that means that this is going to diverge by comparison with the harmonic series. Harmonic we know diverges, and since this series is bigger than the harmonic, it's diverging even more than the harmonic. So we can say that the absolute value version of this thing is not going to work out. So we're not going to converge absolutely here. But we still might converge conditionally if we put the alternating piece of this back in. We see in that case that we do have a series whose terms alternate, and this piece here decreasing with limit to 0, they're saying that we're alternating and decreasing an absolute value to 0. So this meets all the conditions of the alternating series test, which tells us that this is going to converge conditionally by the alternating series test. So that ends up being choice B. For this problem, we want to know which of these series is absolutely convergent. So let's start with the first one. We're going to consider the absolute value version of this, which is just 1 over k. That series is the harmonic series, which we know diverges. So this is a no. Moving on to the next one then. This one, well, I don't really know. We could probably use some kind of comparison test. This might require the integral test. This just looks yucky. Let's come back to this one later if we can't find something that is absolutely convergent. This next one. So this is kind of interesting. Cosine, as you increase the value of k, keeps oscillating between the values of -1 and 1. And since we don't have any pi thrown in, we're really hitting all the values in between -1 and 1 at this point, so even some decimal values. So this is always going to give us back, if I take the absolute value, if I consider the absolute value version of this, this is always going to give us back obviously something that's positive, or at least no smaller than 0. We're also getting something that is going to be at most 1 in the numerator, and this stuff down here, well, since I have a larger denominator than k squared, this would end up being actually a smaller overall fraction than a k if I had a k squared on the bottom. So let me just write it out what I'm talking about here. So this whole thing is positive if we're taking the absolute value version of it, and this whole thing is going to be less than or equal to 1 over k squared. Again, cosine of k can't be more than 1, so at the very least we're breaking even in the numerator, and we have a larger denominator, so that means a smaller overall fraction than if we just had a k squared down there. So because I just found something that, so since my original series is less than 1 over k squared, and 1 over k squared converges because this is a p-series with a p-value of 2, which is greater than 1, that shows us that this thing is going to converge absolutely by the direct comparison test. So we've found our answer choice. If you look into choice D a little bit further, you'll see that choice D is a lot like choice A. You could compare it to something like choice A, and it's still going to diverge absolutely and converge conditionally. So choice C does end up then being our answer for this one. On this problem, I want to know which statement about this series is true. So they talk about whether it can be shown to diverge or converge with comparison or limit comparison or alternating series test. So the thing you really need to know with all these comparison tests is that you need to have both the original and the comparison series to be positive numbers, or at least not negative. Since the nth term here is not always positive because we have this alternating stuff going on, that means you can't use any kind of comparison test. So that immediately eliminates choices A, B, and C. Just looking a little further to confirm choice D, this is a series whose terms are alternating, and since the denominator is growing faster than the numerator, we are also decreasing an absolute value to 0. Therefore, this can be shown to converge by the alternating series test. So, choice D. For this problem, we have an alternating series that converges to S. And let's see here. The table above, we've got some values of the partial sum for 4 values of n. So it's 7, 8, 9, and 10 terms. If S of 8, S8, so basically a partial sum with the first 8 terms of this series, is used to approximate S, we want the alternating series error bound. So the alternating series error bound states that if the terms of your series are alternating and decreasing in absolute value to 0, which it looks like this one is, it's alternating, and this 0 less than or equal to AK plus 1 less than or equal to AK, basically saying all the terms are getting smaller. So since we have the conditions of the alternating series error bound met, the conclusion is that the error is going to be bounded by the absolute value of the next term. So basically, if you want to find the error bound, you just need to find the value of the next term in this series. The trouble is, on this one, they didn't give you any specific terms or really any way to just plug things in and find the next term. What they gave you is a bunch of partial sums. But don't despair. If you want to find, so if we use the first 8 terms, we need to find term number 9. If you want to find the value of the 9th term, or at least the absolute value of the 9th term, all you need to do is take the sum of all the first 9 terms and subtract the sum of the first 8 terms. And that difference between those, S9 minus S8, that will actually tell you what the value of that 9th term was. So this is just going to be 0.459 minus 0.157, which if we subtract that, that's going to be 0.302, which gives us answer choice C. For this problem, we want to know which of these series are conditionally convergent, which is to say we want to know which series converge only if we consider the alternating, not the absolute value version of the series. So one thing I notice here is these are all alternating series, and they're all bottom heavy, so these all decrease in absolute value to 0. So since these all alternate and decrease in absolute value to 0, these will all converge conditionally by the alternating series test if they don't converge absolutely by some other test. So really all we need to do is figure out which one of these converge absolutely, and then those are going to be eliminated from our answer choices. So let's take them one at a time. Let's consider first the absolute value version of 1. So there's a lot of ways to figure out the convergence of 1 over n factorial. Probably the most straightforward way is just to use the ratio test. It's a good test whenever you have factorials involved. So we're going to take the limit as n approaches infinity of the n plus 1th term over the nth term. So that's going to be 1 over n plus 1 factorial over 1 over n factorial. Same change flip, this is really n factorial over n plus 1 factorial. We know that n plus 1 factorial is essentially n plus 1 times n factorial. So if we cancel out the n factorial, this is all just 1 over n plus 1. And the limit as n approaches infinity for this thing is going to be 0. Since that is less than 1, we can show that option 1 here converges absolutely by the ratio test. Since it converges absolutely, therefore it does not converge conditionally. So anything with choice 1 in it can be eliminated. So that gets rid of choices A and D. So now we're just going to check out 2 and 3. And if you look at the way these answer choices are laid out, it all comes down to whether 2 works or not. There's no choice for none of these working. So if 2, well, I guess it actually all comes down to whether 3 works or not. If 3 works, then you have to pick C. If 3 doesn't work, then 2 must have been the only one that worked. But we're going to look at 2 anyway. We'll consider 2, because this is a pretty quick one. So absolute value version of option 2 here, that's just 1 over radical n. Now this is just a p-series with a p-value of 1/2. That's the exponent down there. Since that's less than or equal to 1, this is going to diverge by the p-series test. So basically it's not going to converge absolutely because of the p-series test. So it looks like I'm out of room on this slide. We're going to continue on to another slide. But so far, where we are in the action here, we've eliminated option 1, and it looks like 2 is going to be acceptable because we already established it's going to converge conditionally if it doesn't converge absolutely. So really it's all down to whether 3 converges. Stay tuned for the next episode on this problem. So we're back with this problem here, trying to figure out really the only question left now is whether 3 converges absolutely or just conditionally. So absolute value version of this is 1 over n plus 2. And we can look at this pretty quickly, and if we didn't actually have to prove anything rigorously, this is going to behave like the harmonic series, so we know this thing's going to diverge. But if we wanted to show it rigorously, I would compare this to the harmonic series, 1 over n, which, since it is the harmonic series, we know diverges. And what kind of comparison could we use to prove that the original diverges? Well, the original, because you're adding things to the denominator, the original is actually smaller than the harmonic series. Showing that your series is smaller than a diverging series isn't going to help if you're trying direct comparison, so we're going to have to use limit comparison instead. For that, I just need to establish that the original and the comparison are both positive, which they are for all n values. So originals greater than 0, comparisons greater than 0 for all n greater than or equal to 1. And now, just taking the limit of the original over the comparison as n approaches infinity. So original over comparison. Same change flip on that thing. We've got n over n plus 2. And the limit of that as n approaches infinity, we can just ignore this plus 2. So we have n over n, which is just 1. Since that's between 0 and infinity, this shows that the original, just like the comparison series, is going to diverge by the limit comparison test. So that means that there's no absolute convergence then for option 3, which means that it must converge conditionally because we already established that. So then only options 2 and 3 converge conditionally by the alternating series test. So that means we're going to pick choice C. On this problem, I want to know which series can be used with comparison test, which they mean the direct comparison test, to show that this series either converges or diverges. So when you're using direct comparison, you need to figure out whether the comparison series converges or diverges, and then you either need to show that your original is smaller at some point than a converging series or greater than a diverging series. So let's take a look at each of these choices. 7 over n, this is going to be a divergent one. If you take a 7 out of there, you've really just got 1 over n, which is the harmonic series. So this diverges. So in order to use direct comparison, we would need to show that the original series is greater than this series. Is that the case? Not so much. 4 plus sine of n fluctuates between -1 and +1, so this is a numerator that's going to be somewhere between 3 and 5 at any given time, which is already smaller than this numerator of 7. And also, the n squared here, if you have a larger, faster growing denominator, your overall fraction is going to be smaller. So any way you look at it, the original is smaller than this diverging series. So because of that, that proves nothing, which means this is a no, and we move on to the next answer choice. So we've got 3 over n squared. If you take out a 3, this is 1 over n squared, which is a p-series, p equals 2. Since that's greater than a p-value of 1, we know this is going to converge by the p-series test, or at least comparison with 1 over n squared. So the question is then, is my original smaller than this converging series? Well, we've got the same denominator, so that makes it easier to compare. The numerator, again, we said that 4 plus sine of n is going to fluctuate between 3 and 5. So sometimes you might be equal to 3, but you're never going to be smaller than 3. So because the converging series is smaller than the original, that doesn't actually tell us anything about the original. So this one also, we can't really use the comparison test on this one. Taking a look at choice C, this is pretty close to B, but with one key difference. Again, we have the same denominator. This is going to converge by comparison to a p-series of 2. But on this one, looking at the numerator now, again, we said that the numerator of the original is going to be at most 5. So the original is always going to be smaller than or equal to this converging series. Since you're smaller than a series that already is known to converge, you can use direct comparison to show that the original is going to converge. So this one actually ends up being a yes. And we'll just consider this last one just because, well, we're already there. For this one, this is going to, I mean, if 5 over n squared converges, then certainly 5 over n cubed, which has an even smaller overall fraction, is going to converge. However, for this one, definitely 5 plus sine of n over n squared, that is going to be bigger than this converging series. This denominator here is so much faster than n squared. So because we're bigger than a converging series here, this also would not be very useful for using direct comparison. So then choice C ends up being our answer. On this problem, I want to figure out which series can be used with limit comparison to determine if this series converges or diverges. Just looking at this from a choose your champion big picture kind of approach, this series here should behave pretty similarly to the dominant terms in the numerator and denominator, so radical n over n cubed. And if you actually turn this into an exponent, this is n to the 1/2 over n to the 3rd, or n to the 6/2, I guess. Subtracting those, you could reduce this to 1 over n to the 5/2. Now, 1 over n to the 5/2, which is one of the answer choices, by the way, this is a p-series with a p-value of 5/2. So because that's greater than 1, we know that this comparison series converges. So we'll be able to show, if we can use limit comparison, we ought to be able to show that this original series converges. So let's just do that out and really verify choice C here, because it's looking like that's going to be our answer. To use limit comparison, both of the series, the original and the comparison, need to be positive. And if you look at this, the original has nothing but addition in positive terms, so that's clearly going to come out positive if you're plugging in positive numbers. The comparison series has a positive term, nothing in there to make it negative, so that has to come out positive as well for all n values greater than or equal to 1. Next, we're going to take the limit as n approaches infinity of the original over the comparison series. And as n approaches infinity, I am going to do a little champion choosing here. So I'm going to rewrite this numerator up here as just 2 radical n, the dominant term there, over n cubed. And I'm going to leave the denominator unchanged. Now if I do a little same change flip, actually, even before I do that, let me reduce this fraction up here a little bit just to make my life super easy. Why make things harder than I need to? So this is really going to be 2 over n to the 5/2. Okay. Now if I multiply by the reciprocal, I've got 2 times n to the 5/2 over, well, just n to the 5/2 times 1, so n to the 5/2. Those n to the 5/2 are going to cancel, leaving me with just 2. And since 2 is between 0 and infinity, which isn't a very hard standard to meet, that shows that the comparison series and the original behave exactly the same. So the original then is going to converge by limit comparison. Really, the only question here was which of the series could be used with limit comparison. I think we very clearly established that choice C is the one to go with here.